Hello. This is another finite element lecture where we are going to focus on beam elements. We have already discussed truss elements. Now we are going to add a layer of complexity to truss elements to make them beam elements. At the end of this lecture, you will be able to identify nodes and degrees of freedom of beam elements, identify the terms of the equilibrium equation of frames or beam structures, apply correct boundary conditions to finite element models of frames, apply correct forces and moments to finite element models of frames, and finally troubleshoot FE models of frames with singular stiffness matrix error. Why do I need to know about this? Beams are used in many structures and they are subjected to bending. An example is the Gherkin in London, and these beams are subjected to lateral forces which produce bending in their structure. So you may want to design for resistance to bending, or sometimes you may want to design beams for intended flexure or deflection. Beam elements can also predict torsion. Hence, you can use them to design for resistance to torsion. For instance, in the shaft of this rotor, which is subjected to substantial torsion in operation. Beam elements are accurate in predicting bending and torsion, but they are also computationally efficient for modeling structures that are subjected to bending and torsion. An example is this frame, which is holding the weight of the solar panels. So let's first review the assumptions of the beam bending theory, which will form the basis for the formulation of beam elements. In beam bending theory, cross sections remain planar and the same shape, but they can rotate with respect to the deformed neutral axis. So this is the neutral axis and this is the cross section. This theory is the Timoshenko beam theory. Curvature of the beam is very slight, so this angle is very small. In other words, this radius is much larger than the length of the beam. And finally, the length of the beam is much larger than the other two dimensions, so the cross-section dimensions. As a rule of thumb, it should be around 10 times larger than the other two dimensions. Now we use beam elements to build a finite element model for the beam that is shown here. We discretize the beam with beam elements as shown here. So you can see 1, 2, 3, 4, 5, 6, 7, 8 beam elements are being used here to split, to discretize this beam. Each beam element is a mathematical definition or a mathematical model. So here is one of these beam elements shown here. Like truss elements, a beam element has two nodes, node number 1 and node number 2. A beam element is defined by its geometrical properties. So here we have length, cross-sectional area, and the second moment of area, and material properties, which are elastic modulus and shear modulus here for elastic, linear elastic material. All right, so let's focus on one beam element. And as usual, we have our coordinate system, x, y, and imagine z is this axis that is coming out of the plane. So as usual, we have the beam, the element, which is made of two nodes, and they are connected. So this is a beam element that we use to discretize our structure. So this is node number 1, this is node number 2, and for now we just concentrate on a displacement in a plane, so two-dimensional displacement. So this node can have vertical displacement. So we call this one V, and since this is node 1, V1, so this is translation in the Y direction. And this node can also have translation in the Y direction, so that is V2. For now, we do not look into translation in X direction. We will add this complexity later, but just let's focus on translation in Y direction. And then each node can also rotate, because this is a beam, you know, beam, every cross section can rotate as bending is happening. And we call this rotation about the Z axis, the theta Z. And then the positive convention, you know, the right hand rule is that when you rotate your hand, these 4 fingers around the Z axis, your thumb should be pointing towards the positive direction of the Z axis. So this is what we call theta Z1, and this one is theta Z2. All right, so this is rotation about the Z axis for node 1 and node 2 about the Z axis. So these are translations, rotations. So these are degrees of freedom that we have, 2 degrees of freedom on this node, 2 degrees of freedom on the other node. And you know, we have corresponding forces related to these degrees of freedom. So I draw the same element here. And now I'm going to show the forces. So one force is corresponding to V1. So this is Fy1. And then this one corresponds to V2, Fy2. And then we have moments that are related to theta Z1 and theta Z2. So this is one moment, M, Z1. And this is another moment, which we call it M, Z2, right? So now we have nodal displacements and nodal forces. All right, so let's just look at hypothetical deformation of an element. So imagine we have a beam, the same beam element here. This is our beam element. And after we have applied the loading to our structure, it has bent, it has moved. So imagine now we have this shape. All right, so you can imagine that at this point we have had this much vertical displacement, so this is V1. We have had this much vertical displacement here, which is V2. As well, we have had rotation at V1 and V2, right? So rotation is the angle between the tangent to this displacement plot, displacement diagram, and the axis, the x-axis. So this is theta Z1, and this one gives us theta Z2. Right? So at every node, we have degrees of freedom, theta Z1, V1, V2, and theta Z2. But what happens across the length of the element? So you can see here I have the distribution of this vertical displacement across the element. This is something that we can approximate, we can interpolate between the known degrees of freedom, which is V1 theta Z1 and V2 theta Z2. Okay, so in beam elements, the vertical displacement, the distribution of the vertical displacement across the length of the element is assumed to have a cubic relationship with the distance. Let's call this distance x, starting from V1 and going to V2, like x1 to x2. So I can write this cubic function as Vx equals, so we have A0 plus A1x plus A2x squared plus A3x cubed, right? So this is a cubic function, but we know that for this function we have some known values. We have 4 known values. We know the value of v at point x 1, so that is at node 1. So V at x1 is V1, right? We also know V at x2, that is V2. So these are nodal translations in y direction at node 1 and 2. We also know the slope, which defines the rotation at node 1 and node 2. You know, this slope can be defined as like theta z is defined as dv over dx, right? And then we have theta z1. So if we look at theta z at point x1, we have the value of this, and then theta z at node 2 or x2, this is theta z2. All right, so we have 1, 2, 3, 4 knowns based on the degrees of freedom of the nodes, and here in this interpolation function we have a0, a1, a2 and a3. So these are the 3 constants. So what we can do, we can replace, we can put these known values into this function in order to find these 4 constants, and then we can rearrange them to write this function as a function of the nodal degrees of freedom and a function that is just a function of x. We call this a shape function. So here I have rearranged the equations once I've inserted the knowns, and now I'm writing this equation in terms of the degrees of freedom. So these ones, n1, n2, n3, and 4, which are functions of x, these are called shape functions. Shape functions are the basis of finite elements, which you will see later in solid elements as well. Okay, you remember that when we were discussing truss elements, we introduced a concept which was element stiffness matrix, and we worked out what that matrix would look like. So you can imagine similarly, we have an element stiffness matrix for every beam element, but I'm not going to work out how it would look like. Instead, we are just showing how that matrix is helping us to connect degrees of freedom with the vector of nodal forces. So that matrix, which is the element stiffness matrix, would be a 4 by 4 matrix, yes, times the vector of nodal displacements, which is here formed of translation in y direction and rotation about the z direction at every node. And that would be equal to vector of nodal forces, which is now, when we say force, this is a generic definition, which is these forces Fy1, Fy2, as well as the moments are included in the vector of nodal forces, right? Or if you remember, we can neatly write this in a matrix format where we have K small letters. So this is the vector of, this is the element stiffness matrix times R, which is the vector of nodal displacements, equals, oh sorry, this is D, vector of nodal displacement equals R. So that is the vector of nodal forces. So again, you see we arrive at the same equation. It looks exactly the same as what we have seen with truss. When we look at other types of elements like solid elements, again, you will see that this will repeat. The difference is what goes into these vectors and into this matrix. So you know the size of this and definition of them, it depends on the degrees of freedom that you have in your element. Okay, now we are going to extend the element into structure. And as simple as we can do, we can consider structure made of 2 beam elements. So we just add another beam element here. So let's call this one element number 1, and this one is element number 2. And this one now adds a new node with its own degrees of freedom. So let's add this translation in y direction and rotation about the z and of course the corresponding forces here for the same element. So this is element number 1, element number 2, and the node here has the corresponding force in y direction, and the moment about the z-axis. So here moment is written with m, right? Okay, so that would be mz3. Okay, now we have a structure made of 2 elements and 3 nodes. Now we can put this into the equilibrium equation, where you can imagine here, based on the number of degrees of freedom, we can determine the size of the structure stiffness matrix. Here we have 1, 2, 3, 4, 5, 6. We have 6 degrees of freedom. So our structure stiffness matrix is a 6 by 6 matrix, and that is times, we time that by the vector of nodal displacement, which is V1. We can just add next to it theta, which is both degrees of freedom of node 1, V2, theta, Z2, and V3, theta, Z3, right? And then this equals the vector of nodal forces, so the corresponding forces for each of them, Fy1, Mz1, Fy2, Mz2, Fy3, and Mz3. Okay, so you can see the members, the elements of these vectors. Or again, if you remember neatly, we can write it with K capital. So this stands for structure stiffness matrix times the vector of nodal displacements equals the vector of nodal forces, but these are all capital, representing the entire structure for us. Okay, there is an important concept we need to consider when we are looking at structures made of elements. Here I have a structure made of 2 beam elements. They have these 2 beam elements, number 1 and number 2. They are connected at node number 2. We call it a common node or connecting node. But what is important is that when we are using interpolation functions, we should make sure that we are respecting connectivity at these connecting nodes or common nodes. What does that mean? So imagine this is the deflection of the structure of these 2 beam elements after the loading. So you can see at node 1 we have translational displacement and rotation theta z1. At node 2 we have v2 theta z2, and node 3 v3 theta z3. But what is important with this interpolation function is to make sure that when we are approaching node 2 from this side or from this side, we arrive at the same value of v2 and theta z2. In other words, there cannot be a disconnection between these 2 elements when we are approaching node 2 from one side or the other side. And then this can be with respect to the translation, or it can be with respect to the rotation when we are approaching that node. So I show you an example. For instance, if you have used an interpolation function that when you load your structure, it leads to something like this. So node 1, this is the deflection and displacement of node 1, but this is node 2, right? So you see what happened at node 1, node 2. What is happening here is that rotational degree of freedom, that theta z, is not continuous anymore when you are approaching this node from this side and this side. When you're approaching the node from this side, this is the rotation of the cross section. When you're approaching the node from that side, this is the rotation, right? So obviously you can see there is a disconnectivity between these two elements with respect to the rotational degree of freedom at node 2. The same thing can happen for translations. The good thing is that when we are using cubic function to build the interpolation functions for beam elements, that will ensure that connectivity is respected with respect to translation and rotation. So far, we focused on a beam element in two-dimensional space. Now we are going to generalize the beam element into a three-dimensional space. So here is our beam element, as usual, node 1, node 2. But you can see here there are more vectors and arrows. So I'm going to explain them. So here we have translation in x direction. We show it with u, right? So u1 and u2. Then we have rotation about the x-axis. We show rotations here by double arrows. You can see here theta x1, so that is rotation about the x-axis, right? So I should use the right-hand rule. So rotation about the x-axis, theta x1 and theta x2. And we have translation in y-axis, so you can see v1, v2, and as well rotations about the y-axis, so theta y1, theta y2, and then translations along the z-axis, w1, w2, and rotations about the z-axis, which is theta z1 and theta z2. Well, perhaps you remember from beam bending theory that theta y1, this is describing bending in this plane, right? Theta z2 is describing bending in this plate. But interestingly, theta x1 or theta x2, they are describing torsion, right? Torsion about the axis of the beam. So I can now start putting them into the element stiffness, element equation of equilibrium. So how many degrees of freedom do we have here? So 1, 2, 3, 1, 2, 3. So 6 node 1 and 6 degrees of freedom node 2. Therefore, our beam element has 12 degrees of freedom. So the element stiffness matrix, you can imagine it will be a 12 by 12 matrix times. Now we have the vector of nodal displacements, which includes displacements and translations and rotations. So I'm going to write it like U1, V1, W1. So these are translations in this node. And then it follows by rotations, theta x1, theta y1, theta z1. And you can imagine what comes next is the degrees of freedom of node 2. So U2, V2, W2, followed by the rotational degree of freedom. So x2, theta y2, and theta z2. Right, and this equals the vector of nodal forces, which you can imagine corresponding forces for each of these is like fx1, fy1, fz1, mx1, my1, mz1. So you know now mx1, this is the torque, right? That causes torsion. And so on. So I can just write the rest here, which is fx2, fy2. So all the corresponding forces for the second node. Or again, neatly, we can write this as k, small letter, times vector of nodal displacements equals vector of nodal forces. So you see again, this equation of static equilibrium repeats the same way we have seen with 2D beam elements, with truss elements. This looks the same. The only difference is that now degrees of freedom are different, so we have more elements in this vector of nodal displacement and vector of nodal forces.
All right, a bunch of mathematics, but how should we solve problems using beam elements? Well, the answer is that we use a software like ANSYS, but we need to provide the software with the information it needs to solve the problem. For beam elements, we should provide connectivity between elements or joints, which is happening when we are meshing the structure, where we are discretizing the structure. We also should provide properties of beam members, length, cross-sectional area, second moment of area, material properties, elastic modulus, shear modulus, etc. All of these will go into the structure stiffness matrix. We should also provide boundary conditions or known nodal displacements. They go into the D matrix. And we should also provide loads applied to joints, which is the vector of nodal, which goes into the vector of nodal forces. Well, now let's look at a problem. This steel curved beam is embedded at one end, and it is under a vertical load at the other end. I have solved this problem in a separate video, so please watch that video.
Now we are looking at an example. We have this curved beam. Imagine, you remember the lantern problem. Imagine instead of using a truss of 3 members, we use this curved beam to hang the lantern or any other heavy objects. This beam is fixed at the bottom, so built-in or fixed boundary conditions, and there is a load that is applied here. Now we can analyze the deformation of this beam by using beam elements. So we can use beam elements to discretize the whole structure. So if I throw the finite element, the corresponding finite element here, so let's say we have beam number 1, beam number 2, beam number 3, beam number 4, and eventually beam number 5. Yeah, so this is an FE model of our structure. So we have node 1, 2, 3, 4, 5, 6, and we have node 1, 2, 3, 4, and these are elements 1, 2, 3, 4, and 5. And you know we have given boundary conditions. So at node number 1, this is built in, this is fixed. So therefore, all degrees of freedom of the node are fixed. So now you know that a beam element, a node of a beam element, it has translational degrees of freedom. In this case, they are all fixed, so they're 0. And they also have rotational degrees of freedom. So, well, I started with Z, but no worries. So this is X, Y, and Z rotations. Oh, this one should be X then. Equals 0. And then here we have an external force that is known. This is 10 kilonewton. So that would be F. And if we use like our usual convention for X, Y, and Z, yep. So this will be F, Y, 6. Using the positive convention, that force is negative minus 10 kilonewton. And then the other external forces are 0, except from here where we have the reaction at the support. Okay, what I'm going to do now is to put all of these knowns and unknowns into the element, equation of static equilibrium for our element, for our structure. All right, so here we have the structure stiffness matrix. This is what the software will find for you. You don't need to worry about that. Then we have the vector of nodal displacements. So this is going to be a very long vector. Why? Because every node has 6 degrees of freedom, and you have 6 nodes, so 6 times 6, 36 degrees of freedom exist in this finite element model. So if we start with U1, we know U1 is known, V1 is known, W1 is known, right? As well as theta x1 is known, theta y1 is known, theta z1 is known. Is there any other known degrees of freedom? No, we don't know the rest of them, right? The rest of them are unknown. Okay, so I'm not going to write all of them, but you can imagine these will just continue and repeat the same way we have here, like U2, V2, W2, etc. But they are unknown. We don't know the value of them. And this would be equal to the vector of nodal forces here. So here we have this support. So F x1, F y1, F z1. So these are corresponding to these 3 degrees of freedom or translations, as well as mx1, my1, and mz1. Okay, so these are all related to node number 1. These are unknown, right? So these are forces and moments at the support that we do not know how much they are, but we know the amount of deformation at that location, which is 0. The displacement is 0. We also have other members in this vector. So imagine at node number 2, right? We have fx2, fy2, and fz2, right? Do you know how much is fx2? This is the external force in x direction. It is 0 because we don't have any external force applied at node 2. We are not talking about internal force. This is all about external forces. So this is 0, this is 0, and this is 0. And in fact, the only external force that we know of is this one, or Fyx. So it will go somewhere here in this vector, and it will be minus 10 kilonewton. But the rest, moments or forces, they are all zeroed, all the external moments and forces, except from here that we don't know them, and this one that we know the value of. So essentially, this is what happens when you define boundary conditions and you define external loads when you're setting up your finite element simulation.
So the same as we did for truss elements, we can rearrange the equilibrium equation of the structure in terms of knowns and unknowns like this. So this one is the unknown elements of the vector of nodal displacements, and this is the known elements, and similar for the vector of nodal forces. So now we can solve this equation in terms of dx and find dx, and once we have determined this, we can find Rx like this. Again, you should note something very important here. So look at this term. This is the inverse of this matrix because you have -1 here. So that means that this matrix must not be singular.
Similar to truss elements, we have pitfalls with beam elements, especially when we are defining our boundary conditions. If we do not define adequate boundary conditions, our structure will not be in static equilibrium, and therefore the simulation will stop. Often you receive error messages like singular stiffness matrix or pivot in your model. So here are two examples of inadequate support. So here you can see that we are fixing the translational degrees of freedom, but rotational degrees of freedom are not fixed, they are free. Essentially, we have a hinge at this point. So when this force is applied, this whole structure starts rotating. So it becomes a mechanism, something dynamic, and therefore the mathematics will fail, right? So then you will have the error. Similarly, here we have added two additional constraints, which is fixing rotation about the x-axis and about the y-axis, but we have forgotten to fix the rotation about the z-axis, right? And this is exactly the same thing that is happening. We have a hinge here. So when we apply the load, again, it starts rotating in this plane, and it will become dynamic, and the mathematics will fail again. So you should be very careful about the boundary conditions that you're applying to your structure. And as soon as you see errors that suggest that the stiffness matrix is singular, then you should start first checking the boundary conditions in your model. Something else that I have realized sometimes students make a mistake is that when they are meshing a structure like this, they may use truss elements instead of beam elements. What happens if you use truss elements is that truss elements do not have these rotational degrees of freedom. So it means every connection between nodes is a hinge, and therefore this is like a chain. So it doesn't have any resistance to any rotation, and therefore as soon as you run the simulation, it will stop moving on because you have used truss elements. So there are some pitfalls. You should make sure that you don't have a mechanism in your entire static structure, nor do you have any inadequate supports in your model.
In summary, we have learned about nodes of beam elements and their degrees of freedom, which are 3 translations and 3 rotations. We have learned about element stiffness matrix and structure stiffness matrix in the beam elements context, vector of nodal degrees of freedom and nodal loads, 3 forces and 3 moments go into the nodal loads vector. we have learned what are the boundary conditions and loads that can be applied to beam elements. And we have also found one of the problems that we can face, which is singular stiffness matrix. This is related to inadequate support. So next time you have this problem, you should make sure that your structure is well supported. And it is not a mechanism. It has to be in static equilibrium. Thank you for listening to this lecture.